application.
Thank you very much, Stefania, and Francesco also for organizing. And good morning, everybody. So, if the slides. Okay. So we will slow down a little bit our time scales and we move back to fMRI for the next talk. And we look at this from a methods perspective. And I will show you that you can look at fMRI dynamics at very high spatial resolution, in particular at the voxel level. So we all have seen these beautiful waxing and waning of these spatial patterns during resting state. Of course, this is a little bit accelerated. And the usual pipeline, or many pipelines that we apply to this data, will start off with your favorite anatomical atlas to porcellate the brain, and then to get regionally averaged time courses. And of course, then we can do so-called connectivity mapping. We can constitute a functional connectome by computing all pairwise correlations and putting those together in a connectivity matrix. And we like to look at that from a graph perspective, which means that we can identify nodes with the brain regions and edges with those functional connectivities. And we can look at that in the physical embedding of the brain, or more interestingly, usually, in a topological view, which can reveal organizational principles in terms of clustering, modularity, and so on. Now, functional connectivity in this conventional way is a little bit like a single snapshot of a spinning pinwheel. It's like a summary statistic, and it misses all time-varying and time-resolved information, which supposedly is present in the data. And so that's something we like to address in this talk here. Now, the most straightforward way to extend classical functional connectivity into a dynamic version is, of course, to compute it in a temporally windowed fashion. So you take a window of a certain duration W, you slide it over the data. For each window, you compute functional connectivity. And then, as you can see here in this illustration with the two time courses, you can identify moments with negative or positive functional connectivity and maybe look in more detail at those moments in time. So that's very straightforward to implement. For each functional connection, you get one value per window position. And of course, the trade-off there becomes then, how do you choose the window duration? Ideally, you would like to go as short as possible because you like to access fast dynamics. But then you will suffer from low signal-to-noise ratio and also from low sample numbers, so your statistics will suffer. And actually, there's another more fundamental problem from signal processing, which is that you might be prone to aliasing if you choose your window length too short. So you actually need to get rid of low frequencies, which means you actually also might remove useful signal to start with. And as a side effect, this will largely increase the number of extracted values, of course. Nevertheless, if you do this, this gives you beautiful time-dependent functional connectomes. Here you can see three happy, healthy subjects, and you can see how their functional connectivity moves along as they are lying in the fMRI. Now imagine you want to do this at the voxel level. So then the number of spatial locations becomes really huge. If you look at HCP resolution, you have about 100,000 voxels in gray matter. So that would mean that for each temporal window, you get 100,000 by 100,000 matrix. So that's quite big, even for today's computers. In addition, no sparsity. This matrix, by the nature of functional connectivity being a correlational measure, will be very dense. However, mathematically, this matrix will be actually of low rank. The rank will be at most the minimum of the number of spatial locations, so 100,000, and the window duration, W, which is, of course, a lot lower than 100,000. Let's say if you go for 60 seconds in HEP data, will be 80 frames. So the rank is 80, which means it's a lot lower than. Actually, the intrinsic information captured in this huge matrix is not so high. So what we propose to deal with this is to extract what we call a dominant pattern. So basically we go back to the data representation, which is number of spatial locations times all the time points you have, and we extract a segment out of that that corresponds to a window. And then we compute a rank 1 approximation, which is basically the principle of eigenvector centrality. It's the leading eigenvector of the segment of data. And as you have seen in the illustration behind me, this will give you a vector that is the best approximation of the correlation matrix if you compute its outer product with itself. But you don't need to do this outer product, of course. So all that is all captured by the vector itself. So in a way, the correlation matrix is just an implicit consequence of that. So this is the dominant pattern that captures functional connectivity within that window. And then you do that for each window and for each subject, if you have many. So you concatenate all the dominant patterns across windows and across subjects. And you throw those, for instance, in a clustering algorithm. And if you do cross-validation, you can find that with 6 representative dominant patterns, you basically capture all the variability you see in these dominant patterns across time and across subjects. And as you can see here in the sagittal views, you see this opposing pattern that basically opposes default mode or subsystems of the default mode with frontoparietal networks, salience, and attention networks, but in different proportions and in different ports. Actually, we wanted to verify if the differences you see between these dominant patterns are meaningful, and if we, for instance, can induce an atlas from this, an atlas that would be driven by dynamics of functional connectivity. And by a simple binary sign coding of the voxels in the 6 patterns, you can actually identify an atlas, as you see here, which in the end contains 440 parcels. And you can see that they have striking interhemispherical symmetry and other features like that. And actually, to show you a little detail, which is interesting, if you zoom into the thalamus, you can see that within the thalamus, we identify, driven by dynamic functional connectivity, we identify subregions. And then for each label within the subregion, you can see how it reaches out to other parts of the cortex. And again, this is just driven by variations of functional connectivity over time. So for sure, at the voxel level, there is interesting stuff to be recovered. Now, that was the sliding window approach. You can also look at it from a different perspective, and this is called the point process analysis. So again, here we have 2 illustrative time courses. And for instance, we can threshold the blue time course when it exceeds a certain level of activity, and this will identify key events, so-called key events. If you would average all the fMRI frames for those key events when this blue region is above threshold, you get actually an average map that is a proxy for seed connectivity of this blue region. But the more interesting case is when you just don't average, but you throw this into temporal clustering. And then you can identify temporal labels that label these key events. And then for each label, you can compute the average over the associated frames, which are the spatial representatives of the temporal labels, and those are called co-activation patterns, or CAPs. And in a way, again, this is for PCC, you can see default mode network versus opposing networks in different proportions and with different ports contributing to different patterns. Now, there's yet another way of looking at this, but going further onto the point process analysis, which I will call hemodynamic informed transients. And this tries to first take a step back and incorporate some of the knowledge we have about how actually the blood oxygenation level dependent signal we measure with fMRI comes along and which is, of course, through the hemodynamic response. Supposedly, we have an activity-inducing signal that, through neurovascular coupling and the vascular response, leads to the bolt fMRI that we measure. Now, it is possible to deconvolve the measured bolt signal in a regularized way, so to get you back to the activity-inducing signal, and actually then derive, so a derivative in time, compute a derivative in time of this activity-inducing signal, which leads to what we call the innovation signal. And that innovation signal, when it has peaks, positive or negative, that is actually identifying transients in your brain activity. When you have a positive peak, you have a strong transient to activation. When you have a negative peak, you have a strong transient to deactivation. If you apply this to the two time courses at the top, you will get the following innovation signals. So very clearly, most of the time, these signals, they vary around, let's say, noise level. And then from time to time, you have a very strong peak. And actually, you can validate by surrogate data, realistic surrogate data, which is phase randomized in the Fourier domain, that these peaks that you see here are extremely rare under such a realistic normal. So then you can go on with the same idea as CAPS. You can threshold the innovation signals and identify in such a way key transient events. And then again, you do some temporal clustering, which now leads to innovation-driven CAPS. And you can see here behind me one example of ICAPS obtained from a resting state data set. And the hierarchy you also see next to it is actually obtained from their temporal overlap. So the way they are temporally combined gives you this very nice separation between sensory default mode and attentional ICAPS. And you can actually even go back to the data and look when each of the ICAPS comes active, and they can superpose again, as I've said. And you can link them, for instance, using BrainMap or another meta database to a behavioral profile, which gives you an idea what the subject is doing in the scanner at any point in time. So to summarize, dynamics of brain networks are not only possible using EEG, MEG, but also with fMRI. And I would say there are two families of measures around, correlational ones and instantaneous measures. They're both useful. It might depend what is your application and what you really like to characterize. And they can both be pushed to the high spatial resolution, to the voxel level. Now, in a way, that's only the beginning, because now the real game is to interpret whatever you get out of this. And I would say, again, there are two families of techniques here. You can go into observational summary statistics, which could be durations, fractions, dwell times, spectral analysis, switchings, couplings, graph measures, and many more interesting things you can compute out of these dynamic features. But you can also try to go to more advanced temporal models, which will try to capture how actually the sequence can be modeled and understood. And these models might also be generative, which is, of course, really interesting to go further. So take-home messages. Dynamics can be revealed in different ways. At the voxel level, this gets us closer to the rich spatiotemporal structure of human brain activity. In all cases, we see that things are not as easy as we once thought, in the sense that default mode network and others dynamically are clearly fragmented. We also see extensive spatial and temporal overlap between these subsystems. These dynamics are useful, of course, for resting state, but not only. I think also in task and in particular naturalistic conditions, these techniques can add on to our conventional GLM analysis, because obviously they put much less strict assumptions on the timing. And among the challenges, Obviously, the first one would be to explore links in a multimodal way, going into simultaneous EEG or MEG, which can be acquired next to fMRI, so to access faster timescales. Another one is to take into account structural, so diffusion-weighted MRI, to see how whatever we get with functional measurements is mediated by the structural backbone of the brain, and as already mentioned, going towards more mechanistic temporal models of the brain properly or not properly functioning, and explain actually ultimately behavior and also clinical conditions. And let me thank the team in Geneva at Campus Biotech, who, without whom nothing of this would be possible. So thank you very much.